ever since the beginning of the first molecules and the development of life forms in the form of microbes and then humans, which came long after microbes, there has been a relationship between the human species and even the animal species and the microbial world. And it's a fascinating interaction. There's a lot of mutual dependency. I mean, if you look at the recent delving into the human microbiome, in which there's more DNA from microbes in your body, in your gut, in your genital tract, in your skin, in your mucosal surfaces, nose and mouth, than there are your normal cells' DNA. It's sort of an interesting, jolting feeling. But you live together with the microbes. Every once in a while, those microbes can attack you. They're called pathogens. You have pretty good defenses against many of them, but every once in a while a pathogen will break through the defense, particularly if it's a new pathogen from the outside that you've never been exposed to, like an influenza that you've never been exposed to, or some other type of respiratory virus, or even certain bacteria. So it's an extraordinary world. It's kind of, the microbes in our environment will never ever completely destroy the human species, nor will the human species ever or even want to get rid of all of the microbes. So it's kind of a standoff, some mutual benefit, an occasional incursion on your health that you tend to fight back with things that are natural, like your immune system, or that you make, like antibiotics or antivirals. It's a fascinating world.
Do you live, though, with the uncertainty of these microbes?
No, I don't. I mean, as an infectious disease person and a public health person, I'm constantly aware of and have to respond to outbreaks. I mean, we know, I look at the infectious disease world as the established infections, which means you can generally predict from year to year what the morbidity and the mortality will be. So if you look globally and you look at respiratory infections and diarrheal diseases, which are the big killers from an infectious disease standpoint, particularly of young children and older people, people who have infirmities, who have underlying diseases. Then you have things like malaria and tuberculosis and hepatitis, and things where at any given year, you kind of know there'll be 2 million deaths due to respiratory diseases and 1.5 to 2 million deaths due to diarrheal diseases. Those are the established infections. The ones that are equally, if not more challenging, are the emerging infections, where all of a sudden you get a new infection that you've never seen before. In 1918, we had the pandemic flu that killed 50 to 100 million people. In 1981, we first recognized HIV, which has now had over 75 million infections and 38 million deaths. 50 years ago, there was no HIV to our knowledge, and it wasn't a public health threat. Then every once in a while you get a public health threat that's a blip and then goes away spontaneously, like SARS, the severe acute respiratory syndrome, years ago came and went before we had a chance to do a vaccine, before we had a chance to develop antivirals. Some infections reappear in a different geographic location. We've gone for centuries with West Nile virus in Africa and in the Middle East. Then all of a sudden, West Nile comes to the United States, probably because of the ability to fly people, birds, and mosquitoes from one continent to another over the Atlantic Ocean. Because we know that the West Nile very likely came from Israel, if you look at the genetic typing of it, yet it landed in Long Island. So those can be threatening to some people, and in some respects it is a threat. But in some situations, it can be very exciting because it gives you a real feel of this microbial world. And as physicians and scientists, we tend to try and protect ourselves from the incursions of the microbial world without necessarily feeling we have to eliminate the microbial world, because that will never happen. And that would probably be detrimental to us as opposed to being healthy for us. I think it's the extent and the degree of impact that you can have. When you're serving the public is a pretty big constituency. So if you're really a public servant, and a public servant interested in global health, I kind of think of my constituency as the 6 to 7 billion people in the world that could be vulnerable to some of the infections that I study and that I hopefully help to make countermeasures for.
Do you still have a
But there's another very important part of what I do, and that's called programmatic initiatives. When you need to move the field when it isn't yet moving in a direction that you know it needs to move. Let me give you a classic example of that. In the summer of 1981, when I recognized that HIV/AIDS, and it wasn't even HIV yet because we didn't discover HIV until 1983-84, that I knew intuitively that this was going to be a major global health problem. And I even wrote about it back then in 1981 and 82. So in the early 80s, I became director in 1984. In the early 80s, I had to push the field in the sense of saying, we're going to put this amount of money aside, and I want people to start working on this new disease. So you give me a good idea and I'll fund it. I didn't wait back and say, okay, I'll wait till somebody comes in with a new I say, wait a minute, we have to work on this disease. It's a very, very important problem. I did the same thing with the Ebola outbreak.
You felt it was...
Well, as soon as we started seeing the outbreak of cases, I said we have to rush the research to get a vaccine. When we started to see drug-resistant tuberculosis and drug-resistant malaria, I said we've got to start getting younger people, people with new ideas, people with different ideas to get into the field. So it's a real balance of waiting for the ideas to come in and kind of stimulating the field to come in with these new ideas. For me, it's infectious disease, microbial diseases, and autoimmune diseases and immunological diseases. However, the one profound difference between all the other institutes and my institute is that any given day, I could wake up and all of a sudden there's an emergency that I have to respond to tomorrow. So I tell my colleagues, and I used to joke around with Dr. Collins when he was the director of the Genome Institute. I used to say, Francis, you go to bed at night, there's no chance in the world that you will wake up to a genomic emergency the next day. I go to bed at night and I look at the Washington Post and the New York Times and I say, oh my God, we have an outbreak of such and such in wherever, and immediately you've got to turn on a dime and respond to it. So it adds a little extra bit of challenge, excitement, and tension that infectious diseases just pop up. You know, they're called emerging infectious diseases.
Oh, you bet. Yeah, okay.
Although genetic makeup impacts to a greater or lesser degree virtually every disease, it's much less so in the situation of an infection coming in and infecting you. What the genes might do is determine how well you'll respond to a particular infection. For example, and this is it's an unusual example, but it's an example. 1% of the Caucasian population has a genetic defect of the cells that can bind to HIV, the receptor for the AIDS virus, the co-receptor. There's two receptors for the AIDS virus, and they're called co-receptors. There's 1% of the Caucasian population that has a defect in one of that receptor, which means they cannot get infected with most strains of HIV. There are some strains that could still infect them, but most strains of HIV, no matter what they do, they won't get infected.
That's good information.
Well, but that's an unusual situation. Most of us, when you have a virulent infection, doesn't matter what your genetic makeup is, you're going to get exposed and you likely will get infected. So the genetic makeup impacts to a greater or lesser degree. So an example, if you have a certain gene for breast or ovarian cancer, the chances of you getting it are very, very, very high. Whereas if you look at other diseases, it's a what we call multigenic phenomenon. So you may have a genetic predisposition to diabetes, but if you exercise, do not gain a lot of weight and you're not obese, you eat well, you don't have a lot of sugar, you can likely avoid getting diabetes. But if you have the propensity to diabetes and you just don't care for your diet, you don't exercise, you are overweight, you have a much greater chance. With infectious diseases, that ability to control, except for exposure. I mean, obviously, if you decide you're going to go and drink dirty water, you're going to get a diarrheal disease. But just in the environment, it's much more of something you don't have control over. You know, the broad umbrella of control is leading a healthy life. You get good sleep, you eat well, you exercise, your immune system is in pretty good shape. That doesn't mean you'll never get infected, but it means you have less of a chance of getting seriously ill if you get infected, if you're really a very fundamentally healthy person. That's the reason why, if you look at something like influenza, if you look at the mortality of influenza, it's heavily weighted towards elderly people and people who have underlying diseases because their constitution is not able to mount the proper immune response to clear the virus. Whereas a young, strapping, healthy person, they may get infected with influenza or another microbe, but their body is strong enough to be able to fight it very well. That's the reason why there's less of a chance that a very healthy person will have one of the serious complications of these infections. The immune system evolved evolutionarily in response to early creatures and ultimately later creatures like mankind to respond to and defend themselves against the microbial world that's a pathogen. So the immune system is a direct response of evolution to microbes. So the reason the Infectious Disease Institute is also the Institute for Immunology and Allergy is that that immune system, as it has evolved over the millions of years of evolution, is at the one hand the defense department of the body, but on the other hand, since it's so finely tuned, it can occasionally go awry. And by going awry, it's a finely regulated system. And when it gets dysregulated, it can attack the body itself, and you get autoimmunity, such as rheumatoid arthritis, lupus, and other diseases. And it can also inappropriately respond to things like environmental antigens, like pollen and grass and weeds and tree pollen and things like that. So people who have allergies, their immune system is inappropriately responding to an environmental factor that if a person didn't have the allergy, it wouldn't bother them at all.
And are you then funding?
For me personally, science is never every day the Eureka moment. That's nonsense. That never happens. Science is an incremental increase of knowledge that occasionally eventuates into a Eureka moment. But most of the science is slugging it out, getting incremental increases until you say, now we know where we are with that. And it was the same way with, take HIV. I mean, it's a very good example. So HIV, we find out there's AIDS in 1981. The virus is discovered in 1983, 1984. As soon as we discovered the virus, we started trying to both screen drugs to see if they could suppress virus and target the development of drugs against certain vulnerable points in the virus's replication cycle. And it went, the first drug in 1986 was AZT. It was approved in 1987. It took 3 or 4 years for the second drug, and then the third drug, and then the fourth drug. And then we realized that a single drug alone was not good enough. Sooner or later, the virus became resistant. So you had to put 2 drugs together. And then we found that we had to put 3 drugs together. And then we found out that one of those drugs had to really be a powerful one, like the protease inhibitor. And then in 1996 was the Eureka moment, when now the right combination of 3 drugs completely suppressed the virus to the point where all of a sudden it was not detectable, so people could then go on to develop and essentially live normal lifespan. So it started off with the discovery in 1984, 83, the first drug in 87, and then 9 years later in 1996, we had the combination referred to as the cocktail that completely suppressed the virus. So that's incremental, and that's the way science works, right? Yeah.
And
What a thrill it is to discover something that's not been discovered before. And when that discovery is made, it's going to help a lot of people. See, there's discoveries that people do that are inventions that are all great. It all helps mankind. But when you're dealing in the arena of science, particularly in the biological sciences, there's the thrill of learning something that's never been known before. There's nothing like that. And all you have to do is to get people to get a taste of that, and it becomes very addictive. Very addictive. Right.
that's been too.
Science in its purest form is discovery, and discovery is essentially infinite. You don't get all the answers ever. So you never get that feeling that, okay, I've done it, next. You've done it, but then there's, as you say, another question that comes up, or another permutation of what you've done. There's never an end to the game. It's what I refer to as kind of a perpetual challenge when you're a scientist looking for solutions. In me, it's medicine. That's where I ultimately came. So physical sciences, biological sciences, mathematical sciences, they're all a little bit different. I happen to be in the field of biological sciences, but you never have all the answers in biological sciences, particularly in the fields that I'm in infectious diseases. So there's something both gratifying at it, that you get answers, but also challenging and a little bit unnerving. I call it that productive tension that you get. I used to joke with my, and I still do, with my fellows and say, when you're working in science, it's never really Miller time when you say, okay, I'm done, I've just solved everything, now I'll go to something else. There's always that tension that you have more to learn, more to do, more areas to pursue and discover.
It's tough.
It is, it's tough, but it's the same aspect of it that's tough, that makes you feel that bit of uncertainty, is also very stimulated. I joke with people, a little bit tongue-in-cheek, saying that when you realize that you'll never ever know as much as you should know, you got to get over that feeling of inadequacy, otherwise you'll always walk around like you're inadequate. So some people say, and I think that's interesting, that some scientists, I hope not me, walk around like they're really smart and know everything. I walk around with a constant sense of inadequacy, that I don't know enough or I haven't done enough. So on the one hand, the outside world may think that we scientists really think we're the big deals around, and actually deep down is that feeling you need to know more, which is interesting because it's a driving force to get you to learn more.
You must have come from